Now in this lecture we will going to talk about the p-type semiconductor. So when we are talking about the p-type semiconductor, what we say that when a small amount of trivalent impurities are being added to the pure semiconductor, this is known as the p-type semiconductor. So I'm writing here, when a small amount of trivalent impurities is added to a pure semiconductor, it is known as p-type semiconductor. So what it is doing is that when we are adding the trivalent impurities to a semiconductor, it will going to provide me a large number of holes in the semiconductor. So we can say that addition of a trivalent impurities will going to provide a large number of holes in the semiconductor. So I'm writing here. So this addition of this trivalent impurities will going to provide large number of holes in the semiconductor. So I will going to highlight the number of holes, okay, because this is important. So I'm highlighting this number of holes. That means now in the p-type semiconductor you will be having the holes as a majority charge carrier. So we can take an example of a trivalent impurities. So we have got a gallium, okay, so it has got a atomic number 31, and we have got a indium, it has got a atomic number 49. So what we are trying to say is that when these trivalent impurities are being added to the pure semiconductor, or we can say the our intrinsic semiconductor, these will going to provide the large number of holes in the semiconductor. So such impurities which produce p-type semiconductors are also known as the acceptor impurities, because the holes created in the semiconductor and they can accept these electrons. So the vacancy of a hole will going to accept the electrons. Therefore, it is known as the acceptor. Okay, so we can say that I'm writing that further we can see that the holes are created, and to form the covalent bond, they can accept the electrons, highlighting this accept word. Okay, they can accept. Okay, so they are able to take. Okay, they are doing some bargaining and they are taking something. Okay, because they have got a vacancy available. Okay, so when they have got a vacancy available, they are taking something, they are accepting something. Okay, so they are known as the acceptor impurities. They are known as the acceptor impurities. Now we will going to take an example of a p-type semiconductor, and in this we will going to take again a pure germanium crystal. Okay, and we will going to add a trivalent impurities to it. Okay, so I'm writing that I have a pure semiconductor and I'm taking a trivalent impurities, and let's say I'm taking a gallium as my trivalent impurities. So I'm writing here gallium. We know that the gallium has got a 3 valence electron. Now we will be drawing the bonding diagram for this. So I will be taking in center a gallium, and we will be taking its neighbor germanium as a neighbor of a gallium. So I'm drawing this all here. So gallium, we have got gallium, and then we have got a germanium. And now for the sake of completeness, I will be drawing a line. So this will be showing me a bonding pair between the germanium to germanium right now. Okay, so I'm going for the pairing of a germanium to germanium, and now I'm showing it with gallium and the germanium. Okay, so I'm just completing it diagram. Okay, and now what I will be using, I will be using the red color as I have used previously. I will be showing the electron associated with the germanium. Okay, so for the completeness, I am drawing the whole the electrons. Okay, and you can see these electrons are shared with the corresponding germanium atoms also. Okay, so I'm just drawing it. Now what I will be doing, I will be taking a green color and I will be drawing the three valence electron associated with the gadolinium. So you can see that it has done the pairing with the topmost, leftmost, and the bottommost. But since we have got one vacancy available, okay, so I'm writing this vacancy as a whole. And this gadolinium, which we have shown here, is my trivalent impurity atom. So I'm writing here trivalent impurity atom. So you can see that each atom of a gadolinium has fit into the germanium crystal and it has done the bonding with the three germanium crystal, but it has got one free electrons, or we can say one free, not you can see it has got a hole available, and due to this they are not able to complete its bonding. So to complete a bonding they require some electrons in that hole. Okay, so I'm just using a energy band diagram to explain you. Okay, so you can see that again I will be drawing the valence band and the conduction band. So let me draw this as a valence band, and now I'm drawing a conduction band. So this is my valence band. My valence band will going to have more number of holes available, and in my conduction band I will be having a very few electrons available. Okay, so I'm making a few electrons available in it. So I, for the sake of good visualization, I will going to color this. Okay, so you can see I have got a few electrons available in my conduction band. So what we can see from here is that we have to understand some key points related to holes has got predominance over free electrons, okay, because we have got more number of holes available in the p-type semiconductor. Therefore it is known as p-type semiconductor, and we can say that this p stand for positive. P stand for positive. So now let's do the circuit analysis of a p-type semiconductor. So I'm drawing a crystal here, and in this we have seen that the holes will be the majority charge carrier, and I'm connecting the battery to it. So I will be drawing the holes in it, and the direction of this hole will be to the negative terminal of the battery. So you can see the direction will be, this is positive and this is negative. So the direction of a hole will be toward the negative terminal of the battery. Okay, so this is my direction. So I have taken this as a p type. And at the same time, we have got few electrons also available in it. So we will be representing that electrons with the green color. Okay. So this electron will going to move to the positive terminal of the battery. So this is the flow of my current. So what we are saying that positive charge, and we are talking about the positive charge, we are referring it to the p type or a hole type conductivities, and we can say as whole are positive charge. So I'm writing as holes are positive charge. They are directed towards negative terminal. They are directed towards negative terminal, and this will going to constitute a whole current. So I'm writing it, it will going to constitute for a whole current.